Okay, guys, hold off on the equilibrium for now. I hope to have some time at the end of class. I'm going to minimize our buffer prep problem so that we can go into finishing up some review purposes. So, quickly, let's look at round one. So, put away your equilibrium test for me in like 3 seconds, please, so that we can talk about this. So, in terms of the buffer prep, you should be able to identify how to approach a problem by looking at the species present. And so, this was one of the slides from yesterday that I gleaned over because I was starting to show you how to do problems, but anytime you have a hard time starting, you should look at the species present, meaning ions that are present or acids or bases that are present. If there is an acid present and a base present, they have to react, right? And when they react, generally they're going to be reacting fully in a BDA table, like a full reaction, an LR kind of thing. If it doesn't have a significant amount of something, it might just be a icebox, but we'll have to kind of look at the problem as is before we can make that call. So, in the first, I know we did the first rows. B though, B1, how did you guys approach this problem? What kind of problem is it?
So, salt hydrolysis problem.
Right, so you can see that this is a salt, it must break up. So I say salt hydrolysis, and hydrolysis means to add to water. So you have to choose the ion that actually has a reaction with water. And so that's going to be the OCl minus. It's acting as a what?
Base.
Base, because it has the lack of a hydrogen, so it has to add a hydrogen back to make HOCl and OH minus. So since it's acting as a base, you must find the Kb from the Ka for the hypochlorous acid, which is 3.5 times 10 to the negative 8th, and then do what?
Then sulfur.
Or what do you set up with this?
You do your icebox.
Yeah, so you have, whenever you're using the Kb of the K, you're having an icebox set up here. So I'm just going to show you setups right here, because you guys have the answers you can look at. The second one, we may actually have talked about this, but this is the addition. This is the column that has addition of a strong acid. So the ions present are Na plus from the salt, OCl minus, and hydronium, which is the formation in water of a strong acid. Which of those things will react? The cations and cations don't like each other, right? They repel, so they're not going to react. Right, so that's the only thing that you can exchange an H plus with. So you're going to have OCl minus plus an acid yields. This right here is going to be donated, right? So it's going to make HOCl and water. This is an acid-base reaction because this is a conjugate base or a weak base. So this acid-base reaction actually is going to have an LR, which is the, in this case, the small amount of hydronium, and we're going to have an excess amount of this base left over, our conjugate base. But as these things react, and you set up, sorry, I'm trying to squeeze it in this box, you're going to be setting up a BDA table in this one, because they have to react, leaving one in excess. What are you making? You're making what? This weak acid, right? You're going to have a number here that you make. So as you have leftover hypochlorous or hypochlorite and you make hypochlorous acid, that means you have a conjugate base and a weak acid present after the A. So what do you have present here? So a buffer, right? So this is called partial neutralization. So when you have a salt and you do partial neutralization, meaning you have a BDA table and with excess and something made, look and see if it's a buffer. In this case, it is a buffer, so you plug it directly into Henderson-Hasselbalch to find the pH of this acidic buffer. The second reaction, or the third box over here, had sodium ion, hypochlorite from the salt, and a strong base hydroxide. So which is the strongest reaction here? You know these negatives are not going to react with each other. Okay, the NaOH could form, right? You know it's going to immediately ionize back. So there's not actually a true reaction here because you know it's going to make sodium hydroxide and ionize back. This is a combination of a salt and a strong base, which is the KOH that was added. So the strong base rules, and so to find the pH of a strong base, you just do negative log of OH to get your POH. So that one's just our normal POH calculation with the negative log of the concentration of hydroxide that was in this problem. Nothing else, that's it. Last row, what do you have present immediately you should identify?
You have salt and the weak acid.
You have what?
Salt and weak acid.
What? The salt is specific though. The salt includes the conjugate base of that weak acid. So if you have the weak acid and the within the salt is its conjugate base, what do you have?
Buffer.
A buffer. So you're talking to yourself, you're like, okay, I've got these things, I have a buffer. If I have a buffer, what equation do I use to find pH?
The Henderson-Hasselbalch.
Henderson-Hasselbalch, right? So you have to just identify it, and the quantities at the initial have a minimal change through equilibrium, so they are assumed to be equilibrium values as well, and that's what you plug into your concentrations or your moles. The next one is a reaction. So we have hypochlorous acid, we have hypochlorite and sodium ion, and then the top of the column says hydronium or strong acid. So in this one, you have to choose how this reacts. So the strong acid will react with the more basic part of the buffer, which is going to be what? Which is the more basic part of the buffer? HOCl or OCl minus?
VOCl minus.
Right, it has a lack of a hydrogen, so it has to be the more basic part. So these two things are going to react. So when you write out your reaction, you'll do OCl minus plus hydronium yields HOCl, because that's present and it's also forming it, and water. But this one's interesting because you actually have quantities for two of these. You have OCl minus quantity of 0.1 molar and HOCl quantity of 0.01 molar. And the acid has 0.005 moles. Well, this is all in 1 liter, so all of these are actually technically moles. So you have a number on 3 of them initially or before the reaction. So there's a setup between these that actually is a true reaction, a conjugate base and a strong acid. This one is your LR, again, because it's a 0.005 moles. There's such a small amount of it. It's going to consume a portion of the base, and it's going to make more of this acid. So even though it's changing, it's still a buffer because you still have leftover conjugate base, and you're creating more weak acid, so it's still a buffer. So at the end, you're still going to plug it into the Henderson-Hasselbalch. So in this case, sometimes instead of setting up the BDA table entirely, if you read the Buffers Made Easy reading guide, you'll notice that they just look at how much strong acid or strong base is added, and they subtract it from the thing it reacts with, and they add it to the thing it doesn't react with in the initial setup. So I can look at this right here and tell you that the 0.01 is going to become 0.015 because it's making 0.005 more of this because of the strong acid that's added. So this is going to end up being 0.105 moles, and the conjugate base is going to be consumed, a portion of it is, so that's going to be 10 minus 0.005, or 0.1 minus 0.05, which is 0.095, thank you. So this will be 0.095 moles. And if you think about the reaction, you can do that math in your head. You don't necessarily have to set up a BDA, but it's a good process if you need something kind of as a go-to. But once you know those numbers, you plug that straight into Henderson-Hasselbalch. Last one, exactly the same type of problem, except with a strong base. So which is the what are the two reactants in that one? Strong base would be hydroxide. Which of the buffer components would it react with? The acidic component, so HOCl. And then there, you would do a BDA table, Henderson-Hasselbalch. So these were all related to acids. So we have acidic buffers and all these. We use a Ka most of the time. We use a Henderson-Hasselbalch for pH. Guess what round 2 is? You look at round 2? Look at it now. It's all related to bases. So you're going to be implementing a slightly different Henderson-Hasselbalch equation, which is what? If pH is equal to pKa plus log of weak acid and conjugate base, like this, what's the POH version? If you know the opposite.
POH equals pKb plus log of conjugate acid over.
And if you're looking for a conjugate acid, you're looking for the one species with an extra H plus on it, which gives you the identity of the conjugate acid. So you can use that to find pOH easily because you'll have the Kb given for, is this ammonia? No, sorry, I have the Kb given to you good for aniline. And from there you can find pH by just doing 14 minus pOH. Okay, let's do a couple of buffer prep problems. Darn, where clicker is. That's right. So a couple of the buffer prep ones relate to identifying how much a buffer will change pH, how to prepare it, and if you can determine the pH of a new buffer based off your knowledge of an old buffer. Okay, some of these notes are in your packet. Find them for me. They're not in the new packet, the new little sheet that I printed for you. They're not in the notes that I sent to you yesterday. They're in the initial packet for this unit. Because you'll want to see some of the problems on there. And I'm going to kind of select as we go which problems are necessary so that you guys have some common cause to practice with. It's on page 13 in your packet. So what does capacity mean? Something has a capacity. Okay, so a maximum amount I can hold. So the capacity of this room is, I don't know, like 65 people. A bus capacity is 45 people. It's got a maximum it can hold. So when we talk about buffer capacity, we're talking about the maximum amount of strong acid or strong base that buffer can hold. But when it holds it, it actually is reacting with it. So it's actually how much strong acid or strong base it can actually consume to eliminate pH changes. And so the capacity is going to be related to what the buffer is made of, but also how much stuff is in the buffer. So I'm going to start over here. The capacity that the buffer can hold, aka neutralize, is going to be based off the number of moles present of the acid, of the actual conjugate acid and base, or vice versa. So the capacity is based off moles of the weak acid and conjugate base, or weak base and conjugate acid, depending on what kind of buffer we have. So if I had, let's say, a buffer with 1 mole of acetate, maybe in the form of sodium acetate, and 2 moles of acetic acid, and I add a strong acid, how much strong acid can this buffer hold? Looking at my components, okay, how much of this buffer how much strong acid can this buffer hold?
1 mole.
Why 1 mole? Right, and so strong acids are going to react. Strong acids are going to prefer to react with the conjugate base. So I can only add up to 1 mole of this strong acid before the buffer is totally gone, because it would consume that conjugate base entirely, leaving us with no conjugate base, meaning it's not a buffer anymore. How much strong base can this buffer hold? 2 moles, because this strong base, if I add it, it's going to preferably react with the acetic acid, so it's going to be you can add up to 2 moles of it. After that, the weak acid's gone, and we no longer have a buffer. So the capacity is going to be whatever the conjugate or the weak substance can react with. So you can see pH changes occurs when I have 0.1 moles of gaseous hydrogen chloride. This right here just means strong acid again, so you can just consider that hydronium. And we're going to look at that in reference to these 2 below problems, okay? So I have 5 molar of acetic, 5 molar of sodium acetate, and then vice versa. How much strong acid can that first buffer hold or react with, neutralize? This is, remember, I have 1 liter of each of these. Right, so I can have up to 5 moles of strong acid added, because it's going to react with what? With the acetate part, because that's the conjugate base, and I can add up to 5 moles, because this is the same example, right? I can add up to 5 moles of strong base, because it will preferably react with the acetate, right? So this one that's quite a few moles of the strong stuff being added. That's a really high capacity buffer. This one down here, you can see the numbers, we've diluted it by 100-fold. So this one's only going to be able to hold how much strong acid and strong base? 0.05 moles of strong acid or strong base, so the capacity between the 2 differ by 100-fold. Now, what is the pH of each of these buffers? This buffer and this buffer. How would you find the pH? Okay, you could do an ice box and then do what? You'd have common ion, right? Henderson-Hasselbalch you go straight to Henderson-Hasselbalch, simply because this and the common ion here, when you set up an ice, when you do this, plus water, acetate and hydronium. Now, when you do that and you plug these two numbers into initial and you do changes, the changes are not going to be significant on either side. So you actually have the same equilibrium conditions as you do for initial. So go straight to Hendricks and Hasselbalch. So pH is equal to negative log of the Ka for acetate or acetic acid, which is 1.8 times 10 to the negative fifth, plus what? Log of what? 5 over 5, because you have 5 moles of the conjugate, or 5 moles in this case because it's 1 liter, of the conjugate base, and 5 moles of the weak acid, right? So what's the log of 1? Don't do it in calculator. 0. Log of 1 is 0, okay? So this is 0. So at this point, what is the pH? What's it based off of? It's based off the pKa, right? Or based off the Ka value? Can you give me an estimate? Knowing that this is to the negative fifth. What do you know it's below? Do you remember that the exponent determines the pH?
Yeah.
The exponent determines the maximum pH. So negative log of blah, blah, blah to negative fifth means the maximum pH is going to be 5. But since this is a pretty low concentration in that
like
realm,
4.2.
4.7. 4.74 to be specific. If that was like 9 times 10 to the negative fifth, it would be more acidic. Because 9 is really acidic, or is a large number. So it'd be like closer to 4. But since this is 1.8, it's like closer to 5. Because of the inverse relationship. So the actual pH of this buffer is 4.74, okay? What is the pH of the next buffer in B?
Same thing.
Why the same thing?
Because you have equal moles of both.
Okay, so we're just going to do the same setup. We're going to put O5 here and O5 here. So if you know the pKa and you know that your ratio of conjugate base to weak acid is the same, the pH is the same. So both of these buffers have the same pH of 4.74, even though they have different concentrations. So the concentrations are determining the what of the buffer? The pH?
No, buffer capacity.
The capacity. The concentrations determine the capacity. Like we kind of explained earlier, the concentrations here had nothing to do with the pH. Okay, the pH is determined by the pKa and the ratio of these that are present. This is a 1-to-1 ratio, so this happened to have pH equal pK, but the ratio can help determine the pH of the buffer at the end. Okay, so the pH depends on the acid-base ratio, and if it is a 1-to-1, then pH equals pKa, but the capacity actually is going to be dependent upon the concentration, like how many moles I have. All right, so there's 2 factors you know about buffers. You good with that? This information? Okay. So the point of this is if you dilute your sample, right here in purple, if you dilute your sample, what's going to happen to the pH?
No.
Nothing's going to happen to pH if you dilute it, but if you dilute your sample, it's going to happen to capacity.
It gets smaller.
Right, because you'll have less moles present, or if you dilute it so much that you have very little present, you have a huge pH change. But those are your 2 conclusions you should make from capacity. This information is kind of really just related to what I kind of just said, but just remind me, if I have my acid-base combination, it's a 1 ratio from conjugate base to weak acid. First of all, if I add something, what is the conjugate base going to be neutralizing? If I add a strong acid or strong base, which will the strong acid will be neutralized by the conjugate base, and that's how you write out your VCE that way. And if you have your acid component of the weak acid component of the buffer, a strong base is going to be neutralized by that. So just make sure you write out your VCs correctly whenever you're trying to set up your ICEs or BDAs. I don't think there's any more. The only other part here is that if you're trying to create the best buffer and you want it to equally be able to neutralize acid and bases added, you want approximately the same amount of conjugate base and weak acid. So as the ratio approaches 1, meaning it's a 1-to-1 ratio, the ability to neutralize anything added is improved, but simply because you have enough of everything. You have enough conjugate base and you have enough weak acid. If it's like a 1-to-2 ratio, you're going to be able to neutralize a ton more strong base, but you won't be able to neutralize as much strong acid added. So the ratio of 1 is the best buffer because it can work with anything added. Okay, other fun facts about buffers. If you have to
figure out how to prepare a buffer. You don't just, I mean, you have lots of things available to you. You can choose anything. But the best buffer is going to be having a pK closest to the pH buffer you want to prepare. So if I say I want you to prepare a buffer with a pH of 5, are you going to make an acidic buffer or basic buffer first? Right, if I want you to have a pH 5, that's my goal for you. You're going to have to prepare an acidic buffer. And then your choice is, what acid do I want to use? First of all, should you be using strong acids at all? No, because they won't make buffers. So then you have to look at a list of all these Ka values to figure out which is the best weak acid to use. What would be a good weak acid to use? One with a Ka with what power? 5 or 4? 5 would be better, but higher than 4 would be better, only because unless there's one exactly with 5. So a Ka 1 times 10 to the negative 5th would be the best weak acid to use, but we generally don't have that. But there was one I just mentioned, acetic acid, and acetic acid has a 1.8 times 10 to the negative 5th, and that would be a really good acid to choose, right? So now that you have your acid in mind, how do you finish up making the buffer? What do you have to add? We have our weak acid. How do I add the conjugate? In what form? Okay, I could force the buffer formation by partial neutralization, but I want you to put it together. You'd be adding a salt. What salt? Sodium acetate, right? So this example has been like drilled into the ground, but you should know that you can choose your acid and then correspond your conjugate base through the salt that you choose. Okay, so if you're trying to figure out which is if you're from a selected list, I have a list down here, if you're trying to figure out which of those is going to be the best for the formation of your specific buffer you want to prepare, you're going to have to think about the ranges that they can appear, they can exist in. So your best ratio, or your best way to figure out which is going to be your selected acid based off the Ka value is going to be the pH that you want, and then you're going to look at the pKa values listed, and you can choose in a plus or minus 1 range, and that will get you close to your desired pH. You can adjust pH with your ratio of your salt and your acid that you put together. Because if you want, if you know that, and we just talked about this, the pKa of acetic acid, that's 4.74. That's not 5. What do I need? Do I need more of my conjugate base through the salt, or do I need more of my weak acid to make it 5 when I put this buffer together? So if my just straight up my acid as a pKa of 4.74, I'm making my buffer. Which part do I want more of? Right, I need more of my salt. So I need more moles of salt and less moles of my weak acid, and that's how I adjust my buffer to meet the desired pH. So if I want you guys to choose the best buffer, this is on your paper by the way, the best buffer for a 4.3. Okay, if I want you to choose your buffer that are the appropriate acid to make a 4.3 buffer, which ones can you automatically narrow down to? You can automatically take out this one because that max pH is going to be a 3. You're going to have to add a ton more of your salt to make it go up to 4.3. This one's way too basic, right? Very, very weak. So you've narrowed it down here based off your pH or your exponents of 5 and 5. Which of those is going to be closer to 4.3? So give me some reasoning. Guessing is good-ish. Tell me reasoning. What I know you know that these are not going to help you. Why these?
Because the number of fun is bigger, which means that it would be a smaller. It's more acidic.
So 6.4 is bigger than 1.3,
Yes.
which means better acid, right? If you're talking about Ka, better acid, so more acidic, and more acidic means 4.5 and down. This one up here will be 4.5 and up because it would be on the basic side of that range from 4 to 5. So that's a little hard. This was a question on last year 4 exams. So you should be able to choose your acid based off the pH that you want to prepare it as. Okay, so if I did that though, you guys have your calculators. Do what's the pKa there? .15? 19. Okay,
That's my pKa. How do I, or what do I adjust to get it up to my 4.3 pH when I'm preparing this? I'm going to add more of my conjugate base through the adding of a salt. So I might add like potassium benzoate or something like that. Something with the benzoic anion on the end. So I would need more of my conjugate base salt than my weak acid. And the ratio on the Henderson House of that. Okay, let's do that then. This one is a crazy example because I have 15 molar. Deal with it for now, okay? So go ahead and let's start this one together. How much salt do we need? So we're going to look at this in terms of the acid above, so the benzoic acid that we just prepared, to create a pH of 4.3 that we had previously. But it's okay. So I want the pH to be 4.3. And you can see that I have a liter and I have this much of the acid, which was benzoic acid. And we talked just a minute ago about the conjugate base. Benzoic acid is C6H6COOH, and then the salt is KC6H6COO. Okay, so that's benzoic acid and a salt, a version of it. Everybody with potassium. All right, so how do you guys want to start this? So what equation? We did one really similar to this yesterday. Okay, I need the Henderson Hasselbalch, right? And I know it's in a SIG buffer, so I'm going with the pH version. Sorry. I'm trying not to get sick. I refuse. Conjugate base for weak acid. Okay, what do I not know here?
Conjugate base.
Right, so I'm going to call that X, correct? That's the only thing I don't know. Do I know everything else?
Yes.
Yes. How do I find this?
That's 15 mol.
How do you know it's 15? Did you say 15 molar or moles?
Well, either way.
Well, I can't find the molarity of a salt.
Okay.
So let's go with moles.
So moles.
Okay, so this is 15 molar times 1 liter. If it were different in terms of volume, you would obviously have less. We have 15 moles of this crazy acid, right? Lots of acid. I'm going to kind of rearrange these and just solve for X so that we don't have to plug numbers in everywhere here. So I'm going to subtract pK on the side and do 10 to the log. Remember this from yesterday? 10. So you do 10 to the 4.3 minus, what was the, I don't know what that pK is. I do.
4.19.
Thanks. I didn't even write it down. I just put my, like, everything calculator. 4.19. Thank you. So that's pH minus pKa equals 10 to the X. Oops. Yeah, no, 10 is gone. Because when 10 and log come together, they cancel. So that's X over 15 moles. So 15 times this mess, X is equal to, anybody? Good. I got 19.2, but I'll go with you. 19.32. And that's of the salt, but what salt is it?
Potassium benzoate.
Potassium benzoate. And so I would then take that to, if I had to, like, I don't know what 19.3 moles is, I would have to take that to mass. So just go to mass by 1 mole of that is 161.1 grams. And then convert that to grams. Can you estimate that?
Over 1,000.
Over 1,000. It's like approximately 3,093 grams. Okay, so the story behind this question is I came up with 15 molar, and I think about the realistic nature of this. We would never make a buffer, unless you're industrial, right? Make a buffer at that capacity. That is a huge capacity. 15 moles of that plus 19 moles of the salt, it would just be consuming strong acid base left and right? So that's why we dilute everything. We don't have anything that high of capacity. Okay, that's how you prep a buffer. That's how you figure out how to prep a buffer. Based off your given pH, you select your appropriate acid and then your appropriate salt, and then you adjust accordingly with the ratio of conjugate base to conjugate or weak acid. Okay, this is on your paper. Okay, so there are 2 that say you tried. You guys work on those, and then you'll have time to work on round 2. I'm done with buffers, capacities, and prep right now. We'll do more prep Monday or Monday next week.
On the board you are in lab,
The lab practical is buffer prep. We'll be cutting the buffer after we do this. It might be part of your time grade. It depends on it really depends on how it goes.
Are we gonna like speak to
So you don't have to actually use it.
No, you will have 3 hours cooking this food. We're here like for 4 hours and almost 4 hours. So it depends on how the exam goes. If we do the buffer prep's really. And if there's 3 parts to the lab, if I only want you to do, I might only have you do 1 part.
and like lab groups?
In lab groups, yeah. And you'll be able to explore some of the buffer prep. Yeah. And not everybody will, I mean, except for Kevin, everybody will take the entire time.
How much is? I don't know. My thing.
It'll count 2 test grades, but it'll be the first grades on the next quarter because I will not have enough time to grade it before. I mean, I could try, but I'd rather not. Surprise! Your grade decreases right before the quarter is over. I'd rather surprise.
Surprise, your grades low for second semester.
Surprise! Here's your grade. Let's get it up, grade. I don't know when grades are due. They haven't sent us the Huh? Say again.
Are you saying it does typically decrease your grade?
Can't do much.
I don't want
since my test average is already low.
I would say
Test average is already down there, but it's really just getting.
I would say generally it's harder
I know.
because you probably notice on most of the FRQs on y'all's test, I usually give like half credit. I'll say minus half here, minus this here. On the midterm, I have a specific rubric I follow from AP College Board, and I don't vary from it. I don't sway. So if they say you don't get a point, you don't get a point. So it's graded a little harsher.
Oh,
Yeah.
But you guys, you will be so, your multiple choice, okay, this is the part, like, everybody has told me since I first started, like, this is the only time that you will ever sit down and take a 3.5 hour exam. You're not going to do it at home. Let's be honest. You're not going, all right, motivated, I'm going to sit here and do this for 3.5 hours. You're not. So I have to put you in a situation where you'll do it. And this is going to be one of the most valued ones, because afterwards we'll review this, and then afterwards we have electrochem, which is really fun, and then some sort of physical chemistry stuff, and our physical. It's like drawing Lewis dot structures, wavelength, energy, Bohr model, electron configurations, the vapor pressure lowering, freezing point depression, boiling point elevation.
That's good stuff.
yeah, this sounds pretty. Keep
And
going.
then electron configurations, orbital diagrams. Quantum mechanics is the only part that's different. It's like it's basically narrowing down where electron exists in the atom. So you tell me 4 numbers and that's its address. Okay, it's like, huh? We get it in the orbital. Yes. So we'll talk about those science.
Yeah, they were all tweeting about it last night. They were like,
I gave it to them like right after Thanksgiving.
Yeah, well, they all do.
I basically made them adopt an element. They're all new mothers and fathers, and they had to.
Hayden was having.
I said, pick your element wisely.
Ian grabbed the tweet and he was like, I picked the worst element I could have picked.
So there's their picture. There's their physical and chemical properties.
Oh, so it's not that bad. They're just
Discovered.
telling you about that.
That's it?
No, it gets worse as you
Location
go
and
on.
uses.
No, it gets really bad. It gets worse.
Where's it at?
Ties element and no specific.
I came up with this great rubric, and I didn't think about the repercussions of low data on a particular element. So I told them make assumptions, or I said if they wanted to change their element halfway through, they could change it.
It's funny when Hayden came up to me. He had like a merit.
He had americium.
Yeah, and I was like.
And he was like, I picked the worst element. And I was like, you're fine.
Why
Look
would they
at
pick
that.
random weird ones? They're like awesome.
Oh no. Hayden said they had to take that from
Because
me.
they had to, when it was first come first serve, and they couldn't repeat.
Oh,
So-
so people.
Like snatched up some hydrogen and chlorine, and then everybody else was like, what do I choose? I was like, choose anything you're interested in. And they're choosing like Einsteinium,
Bruh,
which-
it's cobalt.
which doesn't have a whole lot of research on it. So.
Choose like something that you can do.
Ooh, but
Yeah.
we'll have that complete here soon.
Bruh.
Anyway, I'm gonna stop bothering you. Do your stuff right
What are
now
we
so you don't
doing?
have to do it later.
Do
this.
You try.
The you try ones. There are 2.
What's the KD of still.
Are we talking about
What's the
Talk
PV
about
ammonia?
Kathleen's element project.
1.8 tungsten and 6?
What did she do?
No, same thing.
Kathleen.
1.8 tungsten. The same as acetate. Or acetic acid, whatever. Just say it.
Oh,
I'm learning.
she had oxygen.
Once again, I'm just adding less units from round
It's not even like, it's not even like
She
stuff
does
we
have
like
one.
really helped with that project. It wasn't like a lot of stuff that we like really helped with until the end. Like the beginning, it was just like go on Google and look at stuff.
So I told Beanie to do. I was like, can you Google your thing?
For all the facts, but after that, it was like electron configuration.
Google is your friend.
Where's that?
Google is your friend.
Google is your friend for everything.
Yeah, but still.
Freezing point depression? What is that? It came with like a freezing point depression. I was like, I don't even know what that is. Get that away from
Delta
me.
T equals Chem.
I have no idea what you're talking about. I didn't remember what molality was until you told us like 2 days ago.
I never understood the line.
Delta T equals.
Oh, well.
See, I kind of remember it. It's like half there.
It'll come back in about March.
Oh,
What is it?
oh yeah.
Oh, I
I don't remember.
We're making up
You know what? I remember making.
K is like the popular.
How many Ks are there?
Like,
Like, I honestly wasn't really for like.
Kelvin, equilibrium constant, kinetics rate, law constant, freezing point depression constant. Yeah. For now, I have something else, but we shall see.
we also have other things like homework.
I'm not going to sleep tonight.
This homework too.
And I'll not sleep tomorrow. I want to sleep. Yeah.
The KB of ammonia is 1.8 times 10 to the negative fifth. It is the same.
Is this acetic acid? Positive.
Yeah, it's like, are you sure of something?
I've used it for a couple years of my life.
The biology.
Yes, I am. Just give me a